Good morning, I'm Manuel Zarzo, and here in Unit 6, Inference in one normal population, today I will talk about the test about the mean. Well, good. The hypothesis test that we are going to solve in this example is the following. So we want to check if the average of the population is 2000 or it is not 2000. So this is the null hypothesis. It's called null hypothesis because it reflects like the previous knowledge of the situation. For example, imagine that we have a machine that fills bottles, and then the machine should be adjusted so that in average the volume is like 2 liters or 2000 milliliters. So that is the null hypothesis. So the key idea is that if m is actually 2000, okay, so if the null hypothesis is true, okay, x will be similar to 2000, and hence, therefore, the difference between the sample mean and the population mean will be around 0. Okay. So the idea is that if this difference is close to 0, so the null hypothesis cannot be rejected, and so the conclusion will be that we should not readjust the machine. But if this difference between the sample mean and 2000 is quite different from 0, so a big difference, so we'll say that we have enough evidence to reject the null hypothesis. So we will say that m is different to 2000, and then the machine should be readjusted. Good, but what should be considered as being similar or not? Obviously, it depends on the distribution in sampling. Okay, the relative distance has to be measured taking into account the variability. Okay, the variability of the sample variance and the sample mean. Okay, this is the way how we measure that variability according to what we explained in previous videos. Well, good. So this is the null hypothesis. This is the alternative hypothesis. So if the null hypothesis is true, okay, then we have that the sample average minus the population average divided by s and divided by the square root of n follows a student t distribution. Okay, good. So if we standardize, in this case, we assume that the null hypothesis is true, so we assume that m is 2000, so we have that equation. We have I'm going to try to put the pointer. So we have this is the student t distribution. Okay, so in tables we obtain that the critical value for 14 degrees of freedom is 2.14. Okay, the degrees of freedom is n minus 1. Okay, so we have to take in this case what is the value n. So n minus 1 is this case. So the critical value is 2.14. So that this area in orange is the sum of both is 5%, but as we have two tails, so on one tail is 0.025, on the other tail is the same. Okay, good. So if the null hypothesis is true, when we make this operation, the sample average minus 2000 divided by the sample standard deviation divided by the square root of n should be a frequent value of this distribution. It means that this value should be between minus 2.14 until 2.14. But if the null hypothesis is false, we'll get a non-frequent value of the distribution, which means that the value will appear on the right side of the tail or on the left side of the tail. Okay, thus, in this case, if in absolute value we get a computed t-statistic bigger than 2.14, we will reject the null hypothesis. Okay, this is the zone of rejection. But in the other case, if it is less than 2.14, the conclusion is that we cannot reject the null hypothesis. We don't have enough evidence to reject the null hypothesis. Okay, this is the zone. Well, in this case, n was 15, so the degrees of freedom was 14. So we apply this, we apply the function. So 1993.6 was the sample average, minus 2000, the sample standard deviation was 19.8 divided by the square root of 15 and minus 1.25. Okay, where is this value? This value is here. So it's in the zone of frequent values. So it's in the zone of do not reject. So the answer, the solution is that we don't have enough evidence to reject the null hypothesis. Okay, so this hypothesis is acceptable. It cannot be rejected. Good. Well, the summary of the test is the following. Null hypothesis m equal to a specific value versus the alternative hypothesis m different. Okay, so if in absolute value this computed statistic is higher than the critical value that we read from the table, from the student's t-table, okay, we will reject the null hypothesis, and if not, if the absolute value is less than the critical value, we cannot reject the null hypothesis. Okay, there is not enough evidence to reject. So this is the summary. You have these formulas in your math tables. Okay, and this is a critical value, which means a value in the student's t-table, so that the probability that the student t-distribution in absolute value is bigger than this critical value is alpha. Remember that the t-distribution has two tails, so this is why alpha, we have to put alpha halves on one side and alpha halves in the other side. Okay, so what happens if sigma is known? It is not usually the case. Usually from the sample we know the sample mean and the sample standard deviation, but in case sigma is known, so instead of the student t-table, we should use the standard normal distribution. Okay, what happens if the null hypothesis cannot be rejected? It means that there is not enough evidence to reject, but it does not imply that the null hypothesis is necessarily true. Okay? Some people can say that there are like two options: reject the null hypothesis or accept the null hypothesis. But we prefer not to say accept the null hypothesis, because it seems that we have demonstrated in this case that m is exactly equal to 2000, and that is not true. When we say, here, it's better to say do not reject, because we had 15 values. Maybe with 15 values we don't have enough evidence to reject, but maybe if we have more, maybe 1000, the conclusion can be different. So when we say do not reject, it does not imply that the hypothesis is necessarily true. This is why it's best to say reject and do not reject. This is the way how it appears also in star graphics. Okay, what is the p-value? It's a concept a bit abstract. The definition that I gave in a previous video could seem a bit difficult to understand, but it's better to try to understand it graphically. So here in this slide, I will show this concept again. So it's called sometimes the observed significance level. Okay, so and the way how it's calculated is different for every kind of test. In this kind of test, p-value is computed as the probability that student t-distribution with n-1 degree of freedom is bigger than the t computed but in absolute value. Okay, well, what does it mean? Maybe graphically is easier. Well, we have the t calculated, which in this case it was minus 1.25. So I have to compute the area on the left side and also on the right side. So the probability to be less than minus 1.25 plus the probability to be higher than 1.25. Obviously, as this distribution is symmetric, the area is the same, so we can make 2 times the area on one side. So look, based on the calculation of p-value, we have this rule. If the p-value is less than alpha, the rule will be to reject the null hypothesis. Sorry. And if the p-value is bigger than alpha, the conclusion will be do not reject. This rule is always true for any kind of test. Okay, so it doesn't matter that it is based on the student t or on the chi-square or on Fishers or any kind of other test. This is a general rule that we have. Always that we have the p-value, we have to compare it with alpha. And based on that comparison, okay, we determine if we reject or not. This is why the p-value, this is why star graphics gives us the p-value, okay, and then we decide the alpha, okay, and then sometimes based on the p-value we can discuss which alpha can be better. Yes, okay. Then what happens, for example, if in this test we have the t calculated exactly to minus 2.14? Okay, so based on the way as I have shown in this slide, if the t calculated would be minus 2.14, then the p-value would be exactly 0.05. So based on this rule, so that would be the boundary between reject and not reject. And what happens, for example, if the t calculated is like minus 3? If it is minus 3, I think that it's quite clear, based on the picture, that the p-value will be less than alpha. And so the t calculated would be in the region of rejection, so we should reject the null hypothesis. So this sentence here is important, okay? So for other tests, the p-value is calculated differently, but this rule, okay, this rule that appears here always is true. Okay, and this is the definition, the same that I gave you in a previous video. I know that it is quite abstract, but try to think based on this graph. Probability of having obtained a computed statistical parameter more unfavorable being true the null hypothesis. Okay, so we assume that the null hypothesis is true. We have obtained, in this case, a t calculated of minus 1.25, more unfavorable in the sense of rejection means on the left side in this case, but also would be more unfavorable if it is positive 1.25 and it is bigger than. So this is why this area is multiplied by 2. Okay, so try to think in this definition and thinking in this picture. Okay, another definition could be the probability of obtaining test results at least as extreme as the result actually observed, assuming that the null hypothesis is true. Okay, this is a bit more mathematical definition that I obtained from Wikipedia. It's basically the same. Probability of obtaining test result at least as extreme. Okay, well, I know that it's a bit abstract. I hope that this picture clarifies the issue. Okay, so, and then there is a tough question that in statistics we have to decide. And in this slide I will try to answer. Alpha is the probability to make an error. Okay, so alpha in statistic, usually we take 5%, but we can take 1% or even less. But by definition, alpha is the probability to make a type 1 error. And then thinking, maybe we should say, if this is the probability to make a mistake, maybe the value alpha should be as low as possible. So should we always take alpha 1% or even less? Well, the answer is no. And here I will explain why. Well, when the null hypothesis is true, we select a region where it's quite likely, with a probability of 1 minus alpha, to find the statistical parameter used in the contrast. Okay, this is the test acceptance region. Okay, and the complementary is the critical region. Okay, so now let's think graphically. Assuming that sigma is known, well, this in practice this never happens, but this is like a theoretical consideration. This would be the distribution of the sample average. The sample average follows a normal distribution. The average is the average of the population, and then we have sigma divided by the square root of n. Okay, so good. And then we have an interval 1 minus alpha, which is the interval of most frequent values of this distribution, and then outside in both tails we have alpha. So if the value is not frequent, we have the rejection zone in one tail and in the other tail. And if we get this parameter in the zone of frequent values, the answer is not to reject. Well, so if we make calculations, So this is the exact limits where we will not reject the null hypothesis. Okay. So being z, alpha halves the critical value obtained from the standard normal table. Okay. But what happens, okay, if the real value of the population is different? Okay. So although the real value m is not m0, okay, we will conclude do not reject in many cases because the sample mean falls in this zone of not rejection with a high probability sometimes. Okay. So by definition, we have beta. Beta is the probability to make a type 2 error, okay? When m is not m0, so when m is different from the value of the null hypothesis, okay? So we have this from the previous slide. And then imagine that m is not m0, so it moves. So it moves to the right, so m increases, okay? And then this is the distribution of the sample average. And then what would be the probability to accept the null hypothesis in this case? That is by definition beta. Okay, so if you remember from another video, okay, beta is the probability to not reject the null hypothesis when it is false. In this case, it is false because it's not m0, so the average has increased. Okay, but although the average has increased, okay, we have in this case, in this example, a high probability of not rejection, okay, and that is beta. So in this case, you can see that as beta is high, and beta is also the probability to make a mistake, to make an error. Okay, so so we have two types of errors, alpha and beta. Alpha is the type 1 error, beta is the type 2 error. Then both should be low, okay? But what happens? Alpha should be low and beta should be low. But if I decrease the value alpha, then beta increases. And then you can see it here. So if the value alpha decreases, okay, so the error in red is smaller, okay? The range of do not reject become wider. So the red error becomes smaller and then the yellow error becomes bigger. So you can see here that if alpha decreases, then beta increases, and then vice versa. And then the only way that we can decrease both alpha and beta at the same time should be to increase the sample size. Obviously, if we have more values in the sample, so we will reduce the probability of choosing the wrong decision. So in the statistic, a tough decision is to work what alpha to work with. Is it better to work with a very small value alpha? No, the answer is no, because if alpha is very low, then the value beta will be high. So the recommendation in many cases is to work with alpha 5% or 1%. Okay, it's usually the case. Never alpha 10%. That would be the probability of an error too much. Just in the case that we have a very, very few values, in some cases we can work with alpha 10%, but never more than 10%. And if we have thousands of data, maybe we can work with alpha even less than 1%. Okay, beta is usually unknown. Yes, and here I finished this video about the test, about the mean.